Okay. Differential equation models. So we just look at several different examples in which we're supposed to model a given application with a specific differential equation, or generic as it would be the case. In this case, we basically use symbols. Generally speaking, we often use y as a dependent variable. K will pretty much, generally speaking, be a constant, especially in these models. And otherwise, these will be modeled. Just these are quick. This is not the most important idea, but it's a good concept when you're first looking at differential equations, because you often see modeling problems at least be utilized somewhat from time to time in any study of differential equations. So, the rate of growth of bacteria in a petri dish is proportional to the number of bacteria in the dish. And I of course try to include the proportionality first, and then into an equation form. The difference between proportionality and equation is generally that you add in the constant to make it an equal sign. The constant of proportionality, as it can be referred to. Now we have y prime of t, which is a derivative form, and is proportional to y of t, because it's just basically its rate of growth is directly proportional to the number of bacteria in the dish, so it's directly proportional to a number. So it just is basically the constant times y of t. So y prime of t equals k times y of t. And very similarly, we have rate of growth of a population of field mice is inversely proportional to the square root of the population. Difference is we have inversely proportional, and it's to the square root. So that implies when you have your proportionality, it's inverse and square root. So square root means you'll take the square root of it, obviously, of y of t in this case. And inverse means 1 divided by whatever you're inversely proportional to. So 1 over, that's one way of putting it. And so when we change this into an equation, we just add in the constant k on top. You multiply constant k into it. So it's k divided by the square root of y of t. Of course, we have a y prime of t is equal to all that. And this continues as you can read them, but the rate of decay, so I put in a negative sign here for how I would work it through. That's the only thing you have to remember when it's proportional to the amount of substance remaining, so just k times y of t, but it's a negative this time because it's a decay. That's how you should view it. And we're assuming in all these problems that k is positive, it's a positive constant, so that's why it's imperative that if k is going to always be, you should always be consistent with how you label, and always, generally speaking, it is assumed, though, unless otherwise stated, that k would be positive, though, as the proportionality constant is positive unless otherwise stated in this given situation. So decay would be a negative k times y of t. And now we have the rate of decay of a certain substance is inversely proportional to the amount of substance remaining. So just inversely proportional to substance remaining would be negative 1 divided by y of t, and then we just have an equal sign, so it's negative k divided by y of t. But here's a more interesting one. We have a cooling type problem. All this information. You have room temperature 65 degrees F. We have a potato that's been cooking for some time. That's just been put into the air, open air. And the rate at which the potato cools is proportional to the difference between the room temperature and the temperature of the potato. So proportionality would be y of t minus 65. And it's cooling, so I add in the negative sign here, negative k times y of t minus 65. Assuming that k is a positive constant. Yeah, cooling would imply some kind of negativity. And now we have one that involves a similar case, where the thermometer is placed in a glass of ice water and allowed to cool for an extended period of time. The thermometer is removed from the ice water and placed in a room having temperature 77 degrees Fahrenheit. And the rate at which the thermometer warms is proportional to the difference in the room temperature and the temperature of the thermometer. So proportionality, it's right here. We have the rate And generally the rate is the y prime of t. I should have specified that, but it's pretty obvious. So it's proportional to the difference in the room temperature and the temperature of the thermometer. So difference in the room temperature, 77, minus y at t, which is the temperature of the thermometer. I should make that obvious, like, that's what it's being represented, you know, y at t and y prime at t. Y prime at t is rate at which cooling occurs, and in this one, y at t, the difference between the room temperature, you know, is a temperature of the potato in that case. And it's fairly obvious if you just follow these, what it's, you know, y at t here was amount of substance. Just keeps on like that, just to make that clear. And again, that's the reason the thermometer thing is just adding constant k, so and so on. It's positive because it's warming. And that's just generally the logic involved in these, and just real quick, a quick one or two physics examples. But interesting, those are the more interesting models. So a particle moves along the x-axis, its position from the origin at time t given by x at t, so it specifies, so use the symbols they specify, send the variables. A single force acts on a particle that's proportional to, but opposite the object's displacement. Use Newton's law to derive a differential equation for the object's motion. So force is proportional to negative x at t. That's our first step we do. And this is a single force acts on the particle that's proportional to but opposite the object's displacement, so that's why it's proportional to negative x at t. So we have F equals negative k times x at t. So we get from that as far as proportionality goes. But there's the Newton's law, even it tells you to do this to get a differential equation for object's motion. So F equals ma, which means, and we also know a equals x double prime t, so it's a second derivative of position function. So F is equal to m times x double prime of t. And x double prime of t, of course, once again, is like the second derivative of the position function. And because the position is position of the particle at any time t is x at t. So we have force equal to two things, negative k times x at t and F equals m times x double prime t. And we just equal these together to get our equation. Negative k times x at t equals m times x double prime t. And I suppose if you really wanted just to be, there's ways you could rearrange this more, but that's basically all you need. This is a differential equation at this point. Because you have, and it's more serious to it, but that's how it works. You have an equation involving derivatives. You know, it's a big part of what makes it and all. But we don't need to get into specifics for this. But there's one more Newton's problem though to look at. Newton's law to develop the equation of motion for the particle in exercise 8. So from exercise 8, if the force is proportional to but opposite the square of the particle's velocity, we can quickly write from this problem that velocity equals x prime of t. That's a fact. Velocity equals x prime of t. That's its first derivative of position. Basic knowledge of physics. F is proportional to x prime of t squared because it's the square. It's proportional to but opposite the square. We have a negative, but wait, that's what we get. F equals negative k. That's the proportionality constant. Negative k times x prime of t squared. So what really matters is this thing here, being able to write this. You can kind of skip the proportionality step if you ever wanted to, ever be asked this. Generally speaking, you can just understand, like, it's just a setup usually. We have some facts. So the more correct form is F equals negative k times x prime of t times the absolute value of x prime of t. They account for negative and positive values both. You need to split up like that. As I say, the negative and positive velocities. But we also know F equals ma, which implies that F equals m times x double prime of t. And when we did this velocity knowledge from, we included that into that just so it's not obvious, x prime of t, because force is proportional to but opposite the square of the particle's velocity. This is basically velocity squared here, but it's x prime of t, because we want everything in terms of the position function. But when we get this thing here, and we also have f equals ma, which is f equals m times x double prime t, and you combine the two equations into one. So you have negative k times x prime of t times absolute value of x prime of t equals m times x double prime of t. Good thing we don't have to solve that. If we were to solve for the original for x to t, it would be a complicated equation. Which is, often that's what the solution is you're looking for, though, is to solve in terms of x to t. So, but we don't have to worry about that. And that's it for this section.